So welcome back. Now the projector is projecting, as people in the audience here were saying. So I muted the projector just so that people could not read all my email. Not there is anything particularly exciting to read, but you never know. The spirit is strong, but the flesh is weak, as we all know. Okay, so I promised you a first introduction to probability as far as discrete mass 2 is concerned. But before we do that, let's warm up again, because I'm sure you have cooled down. I'm absolutely cooled down. It's a little bit cold today in here. So let's warm our neurons up again by doing an exercise that somehow sums together everything that we have seen so far. Something happened here. It was not like this before, but yeah. There you are. So the question is the one that you can all read, and I'm sure that the people at home are very eager now to put their pens and papers and neurons at work. So the question is, I give you a point, and it's 1, 1, 2. And I tell you that there is a line that goes through the origin, 0, 0, 0, with a certain direction vector. And now my question to you is, what is the distance between the point P and that line? Now, perhaps the first reaction is, wow. How can we ever actually solve this type of exercise? At least that would be my reaction. But in fact, I mean, you can solve this exercise simply by using the things that we just learned in the previous part of today's course session. To show you why that's the case, I'm afraid I will have to try and draw something again. So, here's my point P0. Let's say that this is my point P. And let's say that this is the line that goes through P0 with direction vector D. So let me draw this vector that goes from P0 to P. And let me call it U. Now, how could I actually calculate the distance between the point P and the line? Well, what is this distance? How do I measure it? I can take a laser beam, a light beam, and let it go from P in the direction of the line. And what I want to measure is the length of the light beam of my lightsaber up to the point where it hits the line. So I want to measure the length of this thing, of the red thing. Well, I think this picture is perhaps starting to resemble something, isn't it? Okay, because what is this blue vector here? It's something that we might call U1. And it's nothing but the projection of U in the direction D, which we know how to compute. We saw it before. There is a formula for computing U1. Once I've computed, and I mean, you can do the calculations at home, but you know that U1 is actually U dot product D divided by the square of the length of D times D. So we can compute it using this formula. But then once I know what U is, and U is nothing but P minus P0, or in other words, it's actually P because P0 is 0, 0, 0. Once I have U, I have U1, I know how to compute the red vector. And what is the red vector? Well, to go from P0 to P, I can go from P0 by following U1, and then I can go up the red vector. So the red vector is what I'm missing. It's the U2 that we had before. In the name of love, that's what it is. And once I've calculated it, it's easy to figure out what the distance of P from the line is. It's nothing but the length of the vector U2, which you know how to compute. Okay, so the distance is nothing but the length of the vector U2. So if you know how to compute projections, you can solve an exercise like this in a jiffy. Well, this may require some calculations depending on how nasty people are in giving you the vectors, but typically I'm not nasty. I'm not interested in how well you can calculate because, I mean, at the end of the day, the computers can do the calculations for you. What I'm interested in is whether you understand the course material and put it into practice. The calculations are just boring. You can program this machine to do them for you. I'm interested in the concepts, in your understanding, not in the calculations. That's why I will never ask you to do very complicated calculations during an exam, because it makes no sense. Absolutely. I'm not interested in whether you can solve by hand a 10 by 10 system of linear equations. I'm interested in whether you know the row operations. And I don't need the 10 by 10 systems of row operations to figure that out. Okay, so I'm giving you something out. I will not give you a 10 by 10 system of linear equations at the exam. Or even 5 by 5. Or even 4 by 4. Well, I think by induction, I think very soon I will go to 0, but that's another matter. Okay, are you happy with this picture? Then you can fill in the details at home. The message is, if you can compute projections, you can compute distances of points from points to lines, exactly by following this picture here. Now you may ask, okay, what is the probability that I will get a question like this at the exam? But to answer this question, we need to move on to probability theory, which is, thank God, the last topic that we are going to cover in this cocktail course. I mean, this is really like a cocktail. You take everything that you have not seen else somewhere else, and you get this course out, which makes for a fair amount of variety, but perhaps not for a very cohesive narrative. I guess the cohesive narrative is that all of this stuff is of interest to computer scientists. That's the red thread. So what is probability theory? I don't know what kind of explanation you got in discrete maths 1, or whether you got any explanation whatsoever of what probability theory is, but here's a standard definition. It's the study of the mathematical rules that govern random events. Now, it may seem strange to you that there are actually rules governing randomness. By definition, what is a random event? Well, it's something that is random, so how can there be rules to something which is random? Something that happens by chance. Now, you know, what is randomness is not an easy question to answer, because it's one of those things that somehow we believe that we see a random event when we recognize a random event when we see one, just like we can tell that this is a table by looking at it. We can recognize a table when we see one. But if somebody asks you, could you define to me, please, what a table is? Then things start getting a little bit tricky, because you realize immediately that defining an obvious, a seemingly obvious thing is not so easy at all. I'm pretty sure that any definition of table that you could come up with will rule out lots of things that are actually tables, or that can be used as tables. Well, but we do have definition for randomness, or at least several definitions of randomness. One of them is that a random event is one about which we don't know the outcome until we actually observe it. Okay, pulling cards out of a deck of cards is a random event because you don't know what card you're going to pull out until you actually done so. You don't have any knowledge before you actually perform the act and show the result. But you know, that's not the only possible definition. In fact, computer scientists are masters of randomness, or what we actually tend to call pseudo-randomness, because, well, we generate random numbers, but we do so by means of algorithms which are not really random in any way. We simulate randomness. Okay, you did pseudo-randomness? Fantastic. Huh? So what is pseudo-randomness?
It's an algorithm that generates numbers in a sequence that the numbers generated are unknown until you have generated it enough, but it will eventually loop around to itself.
Okay, so I got an explanation in the room. I'm sure the people at home, I'm not going to repeat it here, but I'm sure the people at home had their own explanation. That's a reasonable explanation of pseudo-randomness. It's a very rich theory. In fact, actually, nobody knows whether even in nature there are truly random events. But you know, I mean, computer scientists have many different definitions of randomness. Well, many, where many means at least two. So we all have, I think, some sort of an idea of what a random sequence of bits may look like. So for instance, if I ask you, is the sequence of bits 1 0 0 0 0 1 1 1 1 1 0 1 1 1, is it random? Well, I just made it up on the spot. It has a certain probability of occurring, but that probability of occurring is the same for all of the bit strings which have the same length, provided I generate the bit string by, say, flipping a coin and saying, okay, heads means I put a 1, tails means I put a 0 at that point. But if you think about it, this assigns the same probability of occurrence to strings like the one I mentioned before, which I can't remember what it is, and the string 1 1 1 1 1 1 1 1 1 1 1. Is the string 1 1 1 1 1 1 1 random? One of your colleagues is saying yes. But if I start saying 1 1 1 1 1 1 a million times, what do you expect comes next? 1. Okay, it depends on how I generate. Suppose I'm using some kind of algorithm, like your colleague said before, to generate the items in my bit string. And you've seen a billion ones. What do you expect next? It's sort of natural to assume that the next one that comes around is a 1. It may not be true, but you kind of expect it. And you know, there is a definition of randomness, which is due to a guy, a Russian guy by the name of Kolmogorov, that is of importance in computer science and is particularly cool for us computer scientists. And it's a definition that explains why we don't think of the string 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 repeatedly as being random, whereas the string that I uttered before, which was complete bullshit, was sort of random sounding. You know, its definition of randomness is based on the length of programs that you need to generate the bit string. Think of the string 1, 1, 1, 1, 1, 1, 1, 1. Well, you need a very short program to generate a string which is of ones arbitrarily long. I mean, say 1 billion ones. The string, the program will just say, for I that goes from 1 to 1 billion, print 1. A one-line program. That string is not random. Why? Because there are programs, very short programs, to generate it. Whereas Kolmogorov's definition of randomness say that the string is random if and only if it is shorter than any program that can generate it. It's extremely cool if you're a computer scientist because it relates randomness with programs. Unfortunately, we are not going to look at this stuff because it's way too advanced for this course, but I had to mention it to you simply because it's so cool. And perhaps in a future life and in a future course, you will look at this. It's something called Kolmogorov complexity. Now, as it so happens, Kolmogorov actually was one of the guys who systematized probability theory. What do I mean by systematizing? I mean that he gave it an axiomatic formulation that ruled out paradoxes in probability theory. And you know, in probability theory, there are lots of things that look reasonable and that instead are bullshit. And it gets to the point where you can find paradoxes. Now, why are you seeing probability theory in computer science? Well, the reason is that you can find it anywhere. And this is just a small sample of topics in computer science where probability actually plays a role. Algorithms, randomized algorithms, and not just random number generators. Software testing. You know, I hope you test your programs. Raise your hands if you don't test your program. Okay, some of you are lying, but that's another matter because we never have time to test our programs, but we should. And you know, sometimes the most efficient way or the most brutal way of testing your program and to find bugs in it is to test it randomly. Okay, there are all kinds of systematic ways that you learn about in software engineering about how to generate good tests. But you know, sometimes the fact of the matter is that it's much more efficient just to test your program using random inputs. And you know, random inputs will exercise paths in your programs that you never dreamed to test in a systematic fashion. And you know where the errors actually usually lie? They lie there, in the odd situations that you never thought about, but that you should have thought about. Communication protocols, IEEE FireWire, or any other communication protocol that you use every day. Randomness inside. Sometimes the protocol is going to toss coin to decide what to do, a coin to decide what to do next. Shall I wait for the delivery of this message or shall I time out and resend it? Well, sometimes you just toss a coin. Decision support systems. How do you know, for instance, what kind of bug the printer is experiencing right now? Well, there are something called Bayesian networks inside that will tell you what is the most likely source of the bug that your printer is experiencing. How does your spam filter decide that the next message that you receive, whether it's spam or not? Probabilistic decision making. Note, probabilistic. It cannot tell for sure whether it's spam or not, but it will make a probabilistic decision that will say, okay, it's 90% spam based on what you marked as spam before, so I will put it in your spam folder. That's where all the messages related to this course go, but that's another matter. Machine learning. I mean, it sounds like a very cool topic, isn't it? Machines can learn. But you know, under the hood, it's all statistics. Well, but modern statistics, which means algorithms that deal with statistical probabilistic data. So it's the probability theory and statistics that computer scientists like you do, not like sort of the old stuffy statisticians from 100 years ago. Coding theory, control theory, anything, it's everywhere. And that's why there are dots of dots there. And that's why you should know about this stuff. Performance evaluation of your programs or computing systems, it's all based on statistics and probability. Okay, are you motivated enough? Hope so. And in any event, you're motivated because this is stuff for the course, so it may come at the exam. I've already told you about machine learning. That was one of my exhibits. There are courses that you can take in the future. Make no mistake, there is a lot of math there. Machine learning is a math course, but with tons of applications, especially now in the world of big data. Well, how do you analyze big data? Statistical methods based on algorithmic statistics, that is to say, computer science. But it's all about probability and statistics running on a machine. So big data is probability theory, based on probability theory. Primality testing. You know, now we have deterministic, fairly efficient algorithms to check where a given number is prime. That's important for cryptography. Why? Because, well, RSA is based on prime number and the hardness of factoring numbers into primes. We don't know whether it's really a hard problem. It's just a conjectured hard problem. And it's certainly pretty hard even for very fast machines these days for very, very long primes. But for a long time, and in fact, even now, the most efficient way of testing for primality of numbers is a probabilistic algorithm that goes back to a guy called Michael Rabin and his collaborators. The idea is that you forget about being 100% sure that the number is prime. You only want to know whether it's prime with a very, very high probability. And you run a very quick probabilistic test that will tell you that with probability, say, 90%, this number is prime. Since the test is very quick, you run it again. This will tell you, perhaps, that the number is 99% prime. But then you run it again, 99.9% prime, and you keep going. You can afford to do very quick tests repeatedly, and the probability that the number is not prime, if it isn't, will rapidly become very, very close to zero. And that's good enough, if you ask me. Okay, woof, enough of motivation. Now I want you to do some work for me. I want you to talk, because my throat is getting a little bit dry. So let's recap some stuff that you definitely saw last time in Discrete Maths 1 last year in a previous life. What is a sample space? Your colleagues here are saying it's the collection of all possible outcomes that my random experiment can have. So for instance, if I throw a die, my sample space will be the numbers from 1 to 6. What is an event in probability theory? Okay, so it's a... So for instance, let me think about the die throw that I gave you before. Is the outcome an even number? Is that an event?
No, each number is its own event, right?
Well, okay, so your colleagues are saying each number is going to be its own event. That's possible, but it's not the only event. So being an even number is an event because it makes sense to ask what is the probability that the number that you get is even. And in that case, the probability would be what? Okay, you can either get 2, 4, or 6. So 3 out of 6 possible outcomes. So the probability, as your colleague in the room said, is a half. And that's the probability of an event. Now, what you've seen so far, I believe, is the theory of probability where all of the possible outcomes are equally likely. So for instance, if I have a fair coin, I toss it, well, the probability that I get a head is a half. The probability that I get a tail is a half. I throw an unbiased die. Each of the possible outcomes has probability 1/6. But what if the head, the coin, is not unbiased? It has a bias. So in that case, I think the theory that you've seen so far does not apply. So, okay, here are two examples just to refresh your memory of what happens when you have all equally likely outcomes in the sample space. So let's only look at the first one, and then you can do the other one at home at your leisure. Suppose you have an urn with 10 balls in it. You know the 6 are red, 4 are blue. You pick one of them. What is the probability that you pick a red ball? It's 6 out of 10. Easy. Now, what is the probability of obtaining a total of 8? So let's do the other one too. When you roll 2 dice.
Well, there are 36 possible outcomes of rolling 2 dice.
Okay.
Some of them add up to 8. That would be 6 and 2, 2 and 6.
Okay. Okay. And so on. But the important thing is that sort of your colleague here gave exactly the answer. So you have 36 possibilities. In order to calculate this probability, all you need to do is to calculate how many of the possible combination of the 2 dice sum up to 8, and that number divided by 36 is going to give you the probability. Absolutely. Fantastic. But now let's move on to a world where things are not equally likely. Okay, so what is the probability that I'm going to get a Nobel Prize? It's 0. So that's a 0 probability event. But the probability that sort of someone else might get the Nobel Prize is going to be higher. It's going to be non-zero. So it's not equally likely that I get the Nobel Prize and that someone else, super scientist, gets the Nobel Prize. So what do we do in that case? So here's what we do. In general, we define something which is called a probability distribution. Now, what is a probability distribution? It's a function that goes from the collection of outcomes to the interval 0, 1 of the real line. In this course, we are going to look at outcomes, sets of outcomes, which are either finite or they are countably infinite. Okay, as many as the natural numbers. Okay, that's also a departure from what you've seen before. So far, everything was equiprobable and finite. The definition that we are going to see now also works when the set of outcomes is, for instance, a collection of natural numbers. Now, when is such a function a probability distribution? Well, it is a probability distribution if you sum up the probability of all of the possible outcomes, it should be 1. Exactly like you had before. The probability of the set of all outcomes is 1. The probability that you get when you throw a die that you get 1 or 2 or 3 or 4 or 5 or 6 is 1, because you cannot get anything else. You're bound to get exactly one of those. Okay, so for instance, suppose that I have my set of outcomes, which are head and tail. But I have an unbiased coin. So for instance, head can come up with probability 3/4, and tail only comes up with probability 1/4. That's a probability distribution for this set of outcomes. Why? Because the sum of the two probability of heads and tails is 1. Okay, now you may find this strange, but I'm pretty sure that if you go to a casino and you actually start playing a game where there is coin tossing, you can be sure that there is some trickery somewhere. Life is not fair because they want to make money. And they make money, not you. So if you get any idea of going to a casino, don't. Okay, so suppose now I tell you what is the probability that if I toss this unfair coin twice, I get 2 tails. What would your answer be?
1 in 16.
It's 1 in 16, as your colleague said, because the probability of getting tail is nothing but the product of the probability of getting tail the first time and the probability of getting tail the second time. And it's actually a very low probability because the coin is very unbiased. It's very biased, sorry. It's extremely unfair. If you throw it, head comes out 3/4 of the time. So if you get 2 tails in a row, you're extremely lucky. So an event, as usual, is a subset of outcomes, of the set of outcomes. It's a possible set of outcomes. So what is the probability of an event E? The probability is nothing but the sum of the probability of all the outcomes in the set. Okay? And of course, this definition is exactly the same as the definition that you know when all of the outcomes are equally likely. If all of the outcomes are a finite number and they are equally likely, then in order for their probability to sum to 1, well, all of them must have the same probability, so it has to be 1/n if you go on at n outcomes. That's exactly the definition that you knew before. Okay, so let's look at some examples. Suppose that you have a biased die. So it's a die, but not all of the numbers have the same probability of occurring. What I tell you is that the probability that you get a 4 when you throw the die is 3 times the probability that you get any other number. And all of the other numbers have the same probability. Okay, so what is the probability distribution that I'm describing?
4 is 3 out of 8, the others are 1 out of 8.
Okay, so we got a probability master in the audience. So we know that the probability of all of the other guys They're all the same. Let's call it x. And the probability of 4 is 3 times x. Now, the sum of all of these probabilities must be 1. Okay, so what is it that we have? Here we have 5 times x plus 3x. So 8x should be equal to 1. So x is 1/8. Which means that the probability of 4 is going to be 3/8. And the probability of getting any other number is 1/8. Exactly as your colleague computed at lightning speed. This is what in the sci-fi movies an alien would do. After reading the Encyclopedia Britannica in 1 picosecond. Okay, but that's the probability distribution for a biased die. Okay, so let me ask you a different question. And again, I always keep getting back to vectors because you love them so much. Okay, here's a probability distribution over a countably infinite set. You get the set 1, 2, 3, 4, and so on. And now the probability that you see an n when you pick a number at random is 1/2 to the n. So the probability that you see a 1 is a half. The probability that you see a 2 is 1/4. The probability that you see a 3 is 1/8, and so on. Question, is this a probability distribution? Well, okay, this is a bit of a tricky question because to calculate whether this is a probability distribution, you need to sum an infinite number, a countably infinite number of rationals. And the fact is that, yes, this is a probability distribution because the sum of all of these guys is 1. But I'm going to ask you an easier question. What is the probability that if you pick, of picking a number in the set 1, 2k? Well, now you need to sum only finitely many of these guys. So what is this probability? Okay, so let's see. So this is the sum for I that goes from 1 to k of 1/2 to the I. Well, there is a formula for that, and this formula would tell you that this is 2 to the k minus 1/2 to the k. And now I think you can see that if k grows, and it goes to infinity, this quantity here is going to approach 1. So you can do a few calculations just before the break. So if k is 5, say, then you get 31/32 as the sum. That's already pretty close to 1. If k is equal to 6, you get 63/64. If k is equal to 7, you're going to get 127 or 122 or 28. And you keep going. This thing is going to get very, very close to 1 very soon. And of course, it can never go above 1 because this is smaller than this. Now, don't get scared, because I think this is the only example that we will see that has to do with an infinite collection of outcomes. But we will see plenty of examples where the probability of the different possible outcomes are going to be different. So what we're going to see next time round is how to work with non-uniform probabilities. We're going to see how to compute something which is called conditional probability, which is absolutely fundamental for decision support systems. And in fact, it's absolutely fundamental for making rational decisions in real life. Because we all have some idea of the probability of the events in our life, but we should update this probability based on our previous experience. And this is what computing conditional probability is all about. It's the key to making rational decisions. So I hope I got you interested for the next course session, which is on Tuesday. Surprise, surprise. Are there any questions?
Is that random?
The question is whether this course session is going to be random. Well, it depends on how much I drink before the course session. But yeah, I typically don't. I don't even eat. So anyway, I hope it's not going to be random, but you never know. Thanks for the question anyway.